My research is into high energy density physics, and that means we're trying to create matter that's at millions of degrees of temperature, at very high pressures, for instance the same pressure that you might find at the core of planets, or very high densities. A large amount of our work has used what are called wire array Z-pinches. So here we take a tiny cage, maybe 10 millimeters across. Each wire in that would be a few microns thick metal. We take electricity from, say, the wall plug, and we'll take that over 5 or 10 minutes and charge our machines. And then we release all of that energy at once in a fraction of a millionth of a second. So there's then millions of amperes of electrical current, millions of volts. The wires would go solid, liquid, gas as they heat up, and then each wire would turn into a plasma. The magnetic field created by these very large currents would pinch these wires together, then redirects that plasma and implodes it towards the axis. And as this plasma moves and carries all of this energy with it, when it hits the axis, it then starts to radiate large amounts of power, often in the X-rays. The plasmas we create with our wire array Z-pinches are very useful for a variety of different research areas. One research area that's recently become very popular is to look at what's called laboratory astrophysics. The reason we're interested for using these plasmas for astrophysics is that there's often 2 or 3 competing theories. We can only see a certain number of jets with the Hubble Space Telescope, and there's no, for instance, reset button if we miss something that's interesting. Being able to do with the laboratory experiment means that we can then controllably change all of the different conditions, and also give a lot more information then for the people doing the simulations and theory to let them try their codes, to give some validation to the codes which they can then take and look at astronomical objects again. The biggest application for high density physics, so the fundamental application, has been to understand inertial confinement fusion. Everybody wants to create fusion because of course it could be a new energy source for the world. It's vital for the strategic effort as well. But for me, it's looking and trying to understand new materials, for trying to really get to extreme conditions, to make new materials which we can only just start to theorize and simulate now. Materials that are harder than diamond, could store better energy than the batteries we have now. Taking computer chips, finding better methods of doing lithography to allow the computer chips to become smaller, to become faster, to become more efficient. It all starts to tie together in a very nice way. It's just amazingly good fun. We get to play with the world's biggest machines, with the world's best computer codes. We get to regularly blow things up, which is always good fun to try. We're working with people who are the best in the world. We're working in teams which have great friendships, and it is just an amazing experience.